far, we've taken a look at two different ways to derive the Laplace transforms for sine of omega t and cosine of omega t. The first was directly from the definition, evaluate the integral, involved some integration by parts. The second was to take a look at the Laplace transform of e to the I omega t, and then take the real and the imaginary parts. Now, we did that directly from the definition because Formula 1, as it's stated on your formula sheet, assumes that a is a real number, and so the restriction on s is that s has to be bigger than that real number a. In the last video, we took a look and saw that we could extend that to if a is a complex number, a plus bi, s simply has to be bigger than the real part of that. So it would have to be bigger than capital A, which is what I'm calling the real part of this complex number. Okay. Now, I will caution you, the version of 1 that's on your formula sheet assumes that a is a real number, and so it has the restriction that s is bigger than a. So, although we're going to go ahead and use this now, I warned you that if I ask you on an exam to derive the formulas for sine of omega t and cosine of omega t, I said you can't just plug into Formula 1, it's just too easy. So if you're going to look at e to the I omega t, I want you to actually work out what that integral is. Okay, I'm going to show you a third way of finding the Laplace transforms of sine omega t and cosine omega t. This version is not given in your textbook. The other three versions that we're going to look at, two that we've already done and one that we'll look at next, are all in your textbook, either worked out directly in the text or referred to and then assigned as homework problems. This, I'm incredibly grateful to Arthur Maddox of MIT. When I was first preparing this class, I watched the OpenCourseware that they have. He did a lecture series on, it was just a class that was videotaped, and they made it available to the public free of charge. Fantastic resource, the MIT courseware. So I watched his videos of his differential equations course, and this is one of the gems that I took from that. It's basically to use the inverse Euler's formula. So I know that e to the I omega t is cosine of t plus I times cosine omega t plus I times sine omega t. Now, that means that e to the negative I omega t is cosine of negative omega t plus I times sine of negative omega t. But cosine is an even function. So opposite input gives me the same output, so that's just cosine of omega t. Sine is an odd function. Opposite input gives me the opposite output, so this is negative I times sine omega t. Now, I'm just going to copy this one up here, cosine omega t plus I times sine omega t. And now what I'm going to do is I'm going to add them. E to the I omega t plus e to the negative I omega t is the same as 2 copies of cosine of omega t. Notice that the imaginary parts here just completely drop out because they're exactly opposites of each other. How exciting! Cosine of omega t is e to the I omega t plus e to the negative I omega t, all divided by 2. So, rather than writing a complex exponential in terms of sines and cosines, I can express cosine in terms of this complex exponential. Now, I can do something very, very similar if I subtract the 2. If instead of adding things, I subtracted, let's see what I would get. So let me write it out here. I've got e to the I omega t is cosine omega t plus I sine omega t. E to the negative I omega t is cosine omega t minus I sine omega t. If I subtract e to the I omega t minus e to the negative I omega t, if I subtract, the cosines are going to cancel out. I sine omega minus negative I sine omega is 2I sine omega t. So, solving for sine omega t, that's just e to the I omega t minus e to the negative I omega t, all divided by 2i. Very cool. So, now if I want to take the Laplace transform of cosine omega t or sine omega t, I can just take the Laplace transform of this, a sum or difference of a multiple of e to plus or minus I omega t. Okay. And I'm going to go ahead and use the fact that we just determined that Formula 1 will work as long as s is bigger than the real part of the number that I'm multiplying by t. Now, since both I omega and negative I omega are purely imaginary, that's going to boil down to s has to be bigger than 0, because the real part would be 0 if I have a purely imaginary number. And that's consistent with what we've seen, because the other two ways we found the Laplace transform of cosine and sine, we saw that the restriction on s was that it had to be bigger than 0. Okay. So let's actually just do this. Let's go ahead and do it for sine. Okay. So if I wanted to take a look at the Laplace transform of sine omega t, I'm going to say that's the Laplace transform of 1 over 2i times e to the I omega t minus e to the negative I omega t. Okay. And Laplace transforms are linear. So I can take this scalar and just factor it out. So I can say this is going to be 1 over 2i times the Laplace transform of e to the I omega t minus the Laplace transform of e to the negative I omega t. The other part of Laplace transforms being linear is that I can distribute it over addition and subtraction. So I'm going to get 1 over 2i times. Now, applying this formula, I'm going to get 1 over s minus I omega minus, this is going to be 1 over s minus negative I omega, so plus I omega. Okay. And I think what I'm going to do is go ahead and get a common denominator, which will be the product of these two, because essentially what that's going to have me doing is getting rid of basically I'd be multiplying this by s plus I omega and this by s minus I omega, which is exactly what I do in order to get rid of the I in the denominator anyway. Okay. So I'm going to have 1 over 2i times. I'm going to multiply this one by 1 in the form of s plus I omega over itself. So I'm going to get s plus I omega over s squared plus omega squared. Remember, when we FOIL, the outsides and insides cancel, and negative I squared is negative 1 is just 1 times the omega squared. Okay. Minus, I'm multiplying this by 1 in the form of s minus I omega over itself. Okay. So that's going to give me s minus I omega over s squared plus omega squared. So I've got 1 over 2i times. Now I'm subtracting, so let's remember that we've got to distribute that negative. So I'm going to have a minus s, so we'll have s minus s, that's going to cancel out. I omega minus a negative I omega is going to be 2i omega over s squared plus omega squared. Let's cancel that 2i. I'm getting omega over s squared plus omega squared. And remember, the rule was that s had to be bigger than the real part of I omega and negative I omega, which is just 0. And of course, I could do the same thing with the Laplace transform for cosine of omega t. Now, on an exam, if you want to use basically the inverse Euler's formula to write sine omega t and cosine omega t in terms of the complex exponential, you certainly can. However, do make sure you read the directions. I'm likely to say that you're only allowed to use Formula 1 if a is a real number, because the version that's given on your formula sheet supposes that a is real and just says the restriction on s is that s is bigger than a. So that if you wanted to use Formula 1, you would first of all have to justify doing that in the case of a complex number. So I wanted to show you this, but I don't recommend it as what you would necessarily do on an exam, just because the formula that you're going to be given, the version of Formula 1 that you'll be given on your formula sheet that then you're allowed to use without proving, unless you're explicitly asked to prove it as a separate question, that formula supposes that A is a real number.